I'm Roger Hanlon, a senior scientist at the Marine Biological Laboratory in Woods Hole. My training is in ethology or animal behavior, and I am a field researcher foremost. We also do laboratory experiments, and I'll present some of that information to you today on my favorite animal group, the cephalopods. The reason we've chosen this particular subject, signaling and camouflage, is that this is the only animal group on Earth that really has these fantastic and unusual and very unique behaviors. So without further ado, I'd like to really get into the subject right away and introduce this field scene right here, which you'll notice is a little boring. There's just a rock out here and a lot of sand and a small fish is swimming. And there's really not very much happening in this image for quite a long time until now. You see here, this amazing octopus has been on that rock all the time, and now it's gone from fully camouflaged to highly conspicuous, swimming away. And you watch here, it now spreads its web all over, makes itself look larger than it really is, using a high contrast patterning with a large dark eye. And in reverse, you really get a better feel for the dynamics or what are happening. Watch this ring develop around the eye. That's 5 million chromatophore organs innervated directly from the brain. And now you see the patterning occurring in the skin right here. And then I draw your attention right here to the smooth outline of the body. And you notice that it goes three-dimensional as well. So in reverse, you really see the dynamics of what's happening in many important features that really represent camouflage in many animals and dynamic camouflage in this one. So if we look at this carefully, the animal's gone from highly conspicuous to highly camouflaged. And in this case, we call this a high fidelity match, which is to say it looks a lot like the pattern, the posture, the intensity, the color, and even the 3D skin texture of the calcareous algae that's on the rock here. Now, a lot of people think this is what camouflage is, looking exactly like the background. But I want to point out a few features that would bring that idea into question. First, I want to point out that right here, if you look in this image, this octopus can go anywhere on a coral reef or a kelp forest and camouflage. It doesn't matter if it's a fully developed coral reef like you see in the top left corner or anything in between. So these animals can go where they want, essentially. They can develop the camouflage that's needed for that particular background. So camouflage is about visual perception. How does the octopus view that background and make this complicated choice? How does the brain control the skin to produce such a diversity of these visual illusions? And there are many similar questions that one can ask relative to this behavior, and that's what I'm going to focus on in this overview of concepts at the beginning. In part 2, I will go into more detail about the visual control of this, and in part 3 about the skin and the neural control as well. So we'll look at all facets of this particular behavior. So this is the burning question that drives a lot of the work in our laboratory, and I want to give credit to a very large group of very able collaborators. This is certainly not just my work. Now I want to introduce the predator. This is a barracuda that one sees on a coral reef with a fantastic set of eyes, not to mention some pretty good teeth. And these animals have superb vision. And I want to make this point right now that this camouflage system is really tuned to some of the most diverse vision known on this planet. That of teleos fishes or bony fishes, birds, there are diving birds that go after these animals, and even diving marine mammals. And these are organisms that can see polarized light. They have 3 or 4 color receptors compared to our 3. Some of them can see polarization. Many of these predators can see at night. And so there are a lot of attributes of vision that we don't have as humans, but this camouflage system has adapted to many of those. So I want to look at this whole thing as a system, really. Behavioral ecology is my particular main field. We're looking at predator-prey relationships. We're looking at communication. We're looking at the theoretical grounds of camouflage, which have largely been ignored, as I'll point out soon. It's a study in visual perception. What about the 2D and the 3D objects in the background? There's color, there's texture, there's night, there's motion. There are a lot of things to take into account in visual perception. What about the neural control and the motor output of the skin? The optical physics of all this are very important. One has to quantify the light field to know what light is available, and then to quantify the light on the animal to really see how the animal is manipulating the light field through its pattern to avoid predation. Image analysis, quantitatively comparing the animal to its background, is one way that we can measure camouflage. And nanotechnology and material science have a connection here, biotechnology if you will, because the skin of these animals produces coloration and patterning unmatched to any animal that we know of. And the idea is to see whether some of the principles of operation of the skin can be translated to nanotechnology and metamaterials and so forth. And finally, I want to point out art and science. This is all about vision and visual perception, and the artistic communities, in the widest sense of the word, really have a lot to contribute to this biological study. So, rapid adaptive coloration is what this animal group does. And I want to point out that the speed of change and the diversity of patterns that these animals have appear to be unmatched of any other animal group we know of. So we give this a term rapid neural polyphenism. Polyphenism just means many appearances, and each animal can show up to 30 or 50 patterns. It's direct neural control of the skin, and again, I'll emphasize once again, it's attuned to a great many visual systems. So camouflage is something in which most animals have a fixed pattern or slowly changing pattern. In that case, the animals have to go to the right place at the right time, the right lighting conditions, and the right posture to implement their limited camouflage. Changeable patterns like the cephalopods and many fishes and some reptiles and so forth can go anywhere and match the background. Therefore, they have a great deal of versatility. So the slow changing, low diversity animals, as pointed out here, reptiles, amphibians, are very different from the animals that change fast and have a lot of diversity. And maybe we can learn something from this group right here that may apply to all the others. That's the direction we're going. So just a quick word about the cephalopods and why they have such an unusual system. Ancient cephalopods, as depicted over here, really had enormous shells. That's drawn to scale. These are in the fossil record. But through evolutionary time, they went through and lost the shell, achieved buoyancy, locomotion, very complicated brain, a wonderful suite of sense organs, and this miraculous skin that we'll talk about in a moment. But the strange thing right here is that they live very fast. They only live for a year or so. They grow very fast, but they have this incredible nervous system. So it's a very unusual life history tactic. A word about art and science. You can see here we've got a very non-camouflaged cuttlefish. The same animal over here can go very camouflaged. And so if you look at the features that the animals are really dealing with, it really gets down to just 5 or 6 features that are being manipulated continually in the skin in this case. So these features are things that are shared in art, in photography, architecture, landscaping, marketing and advertising, and even biotechnology. So coloration and patterning are all around us. How much do we really understand it? Well, let me go back to zoology for a moment and ask a really rudimentary question, and that is, how many camouflage patterns do you think there are? Not just in an octopus or a fish, but any animal whatsoever. So this is a question that's hardly been asked before, but I will point out that in our case, we've been studying the cephalopods for a long time, and the short answer, we think, is 3, not 50, 500, or 5,000. Those are answers I typically get when I pose this question. And this is a very unusual, counterintuitive kind of answer, and it's up to me to try and give some data to prove that concept. I want to point out, however, that even though there are 3 basic pattern templates, there's a lot of variation on the theme. So here is a uniform pattern, and we will define this as little to no contrast. I don't care what the color or the brightness is, I'm only interested in little or no contrast and the same pattern from one end of the animal to the other. Mottled might be described in this case as small-scale light and dark patches of moderate contrast and some general repetition of the pattern. And of course, on a background that has similar features, would create some nice blending in with the background for camouflage. For disruptive coloration, we now have a very different outlay of large-scale, high-contrast, light and dark components, multiple orientations and scales, here partly to break up the recognizable form, but of course, as shown here on the right background, also creating a fair amount of background matching as well. Now, the idea behind this is that if the cephalopods can go anywhere and hide with only 3 pattern types, that's a big if, is it possible that maybe all animals have just 3 or 4 basic pattern types? And how we arrived at this was to take thousands of pictures of our changeable octopus or cuttlefish, and we said, what are we going to do with this mess? Is there some sense to this? And we were able to sort of bin it into 3 or 4 categories. That's where we came up with this. So the animals are teaching us the answer. We're not dreaming it up sitting in our desk back in the lab. So with that in mind, I've gone to the trouble, and many of the students in my lab have, to give some examples of uniform patterning. So we've gone all the way from primates to amphibians to reptiles to fishes to insects, and there's a lot of uniform coloration out in the world. We all know that. And on a uniform background, some degree of camouflage will be achieved. Mottled is another kind of general resemblance. Again, you see here are birds and other similar groups that I just showed you. Doesn't matter if the animals are big or little or wet or dry, you can find a lot of these coloration types throughout the animal kingdom. And finally, disruptive, which is quite unusual and exaggerated perhaps the most in a panda bear or an orca whale. And these are animals that, look, the refrain here is that there's an enormous amount of bright white and brightness, large scale, high contrast. And again, in the right background, these can work. Let me get an extreme example. You take a panda bear. The panda bears are sometimes arboreal. If that panda bear is viewed up towards a bright morning sunlit sky, your retina washes out with the brightness, you have deep shadows, and now this becomes bright sun, this becomes dark shadow. You cannot connect the dots to recognize that that's a bear. So that's one of the ideas behind disruptive coloration. Now that said, in the biology circles, the hardest definition we're trying to support among the zoologists is whether or not disruptive coloration really works in that manner. It's hard experimentally to sort that out. The big significance in our view of this is that if in fact, and it's not fact yet, there are only 3 camo pattern types, then the implication is that the amazing diversity of visual systems on this planet can be tricked in some degree by just 3 or 4 pattern types. So we need to go some way towards proving that. So in this publication right here in 2007, I posited some of these ideas based on our collective work on cephalopods and whether or not this might apply on a larger scale. Well, to say the least, this is a provocative idea. It's been controversial, and I would counter by saying, well, it's testable to some degree. So I will present some of those tests today, especially in part 2, but I'll outline how we go about that now to get the ball rolling. So back to this fundamental question of what is camouflage. Glibly, I can say that it's probably one of the least studied subjects in biology that we think we already know about. Everyone thinks it's looking just like the background, and I've already hinted that that's probably not what's going on most of the time. I'm going to give an example now of a little more film, and this is an octopus on a coral reef. It's moving. Now, movement gives away camouflage, as you well know, and the idea is that when this octopus is foraging, it changes its pattern. We've even measured it about 170 times per hour, so a search image would not be formed by a predator watching it. See that black and white high contrast? It's very, very easy to see from a great distance, but now, as it gets on this promontory, it stops and settles and puts on this stable pattern. So I ask a basic question here. Does this octopus look exactly like any of these corals that are surrounding it? And I think you'll agree that the answer is no. It doesn't look exactly like any of them. But it has achieved a really fantastic degree of camouflage. So to us, this is a far more interesting situation. It's a far more common situation because coral reefs have hundreds of kinds of corals and algae and sponges and bryozoans, and we don't know how many rocks. So it's not a very sound idea to think that animals would look just like the background to achieve camouflage. So we can try to push that idea forward, and we'll help the analysis a little bit. In my view of looking at this animal has come up with a generalist solution, a pattern that works to a very complicated visual challenge. What was it looking at in these corals that made it put that particular pattern on? That's really important for us to understand. So with this idea, we want to move forward and try and analyze the subject a little differently. So what is camouflage? Background matching, I've already mentioned that. And the first video I showed you was a high fidelity match that happened to the octopus, looked a lot like the algae. But I've just now shown you the more common case of the generalist match. So statistically, you cannot find a statistical match, a true one, in any of the camouflage images we have, and we've got tens of thousands of them. So exact matching is really not the greatest term. Disruptive coloration, which I've also mentioned here, also takes care of some anti-detection, but it disrupts the recognition. And this is done partly by these features of internal contrast and edge design. It wants to get rid of its outline edge and mask that, create false edges so that you don't know where the animal actually is. It's one of the main tricks they use. And masquerade, which has to do with looking other than itself, whatever it is, that might be mimicking another animal or some kind of deceptive resemblance to a piece of algae or a rock. Many animals have tricks like this. Now, I won't pretend to say that all of the camouflage literature can be summed up in these three items, but they are the general ones. And I think that you can use these as a way forward if you want to study the subject in a little more detail. What we are after is trying to quantify camouflage, and that is a really daunting task, and there's no book or paper to go for that. There are a few worthwhile books for those interested. This is the real classic, Hugh Cott, 1940, Adaptive Coloration in Animals, is really a prescient piece of work, very thoughtful, and a lot of the ideas in there are ones that we all pay a lot of attention to today. More recently, 2009, there was a equivalent of a book, numerous articles in Philosophical Transactions of the Royal Society, and then coming out just now this year in 2011, this book on animal camouflage. So the interested reader can move in that direction. So let me introduce this jigsaw puzzle that you see in your screen, and I'm going to pull some of these bits together, and we're going to build a cuttlefish. Now, that cuttlefish has a disruptive pattern, as you see here, and you see this bright white marking and the head bar, and there are about 11 components that the body can be broken into. So the animal doesn't have an infinite number of things that it can show. It's got X number of building blocks that physiologically it turns on in the skin, and it takes different combinations to create any one pattern. So that's what you see here. Now, it doesn't look very camouflaged until we put it on the right background. So we go from this to that, and you begin to see some of the magic going on. The actual edge of the animal is quite hard to see, and our eyes are drawn either to the bright white spot or to the sharp edges here. So these are some of the tricks we think are characteristically happening. Now, the real goal here for all of us is to understand camouflage well enough and to understand backgrounds well enough so that eventually we can predict when an animal goes there and stops, it's going to deploy X pattern, and to try to do that qualitatively and quantitatively. That's really what we're looking for. Now, we're a long way from that, but we do have a few operating principles that can help us. So that brings us to this key subject. How does this animal move around, look at this background, and so quickly achieve adaptive coloration? So experimentally, we're lucky because the cuttlefish or an octopus is an animal whose primary defense is camouflage. So they are just genetically driven to camouflage no matter what background you give them. It's an astounding feature that we can exploit in the laboratory. And the concept that I'm really going to posit to you right now is that if there are only 3 basic pattern types, then to achieve this fast change occurring in less than a second, they can't have a brain the size of this room to analyze all that information. We think that they're ignoring a lot of the visual information and looking just at 1 or 2 key attributes of the background to turn each of the pattern types on. That could account for the speed, so consider it a working hypothesis. Okay, so the animal's eye is rather unusual. When you look at this eye, if you look in cross-section, it looks very much like the cross-section of my eye or your eye, but it's actually arranged very differently. But I will point out in the brain of this animal, these kidney-shaped things on the brain are all optic lobe, and the center part here are 20 or 30 other lobes of the brain. This is clearly a visual animal, but we don't know exactly what those lobes are doing. So we have a large complex eye, huge optic lobes. They have very keen visual acuity. Curiously, they can see polarized light. We cannot see polarized light, not that many animals can. They can see very well at night. I'll show you some data on that. Yet, curiously, they seem incapable of color vision, which has some ramifications for the idea of colorblind camouflage, because their predators do see color for the most part. So how do they get the color right? All right, here's the experimental design. So you see in the top here, we've got environmental information which we present to the eye of the cuttlefish. And then, because it's genetically driven to display some kind of pattern, we've got our 3 pattern types right here. And bear with me, let's see if it really is just 3 pattern types. And the idea is we put a cuttlefish in a uniform background like this, we give it a non-uniform background like that, and we give it a non-uniform background of different scale and different contrast, and the animal is now morphed from uniform to mottled to disruptive. Now, what are the cues there? The cues here are black and white, small scale, moderate contrast. The cues here change by spatial scale and by contrast. What are they really paying attention to? Well, first let me show you a dynamic example of the change on a real substrate rather than the strange ones I just showed you. So here's a cuttlefish on a sandy bottom showing a nice uniform background. And somewhat cruelly, we pull the rug out from under it, and it sees this non-uniform background and immediately begins to change its pattern. And it settles, a little upset because we moved it, but you can see it goes into this mottled pattern. It would get rid of that little white square if we gave it just a moment, because that's a disruptive mark. But instead, our special talented 3-handed technician reins in white rocks from heaven. And look, the cuttlefish looks at the white rocks and specifically goes over and changes its pattern dramatically into a disruptive pattern. So I think you can understand if the animal had stayed here, the camouflage would have been very good. Would have been mottled on a mottled background, and that was effective. But there seems to be a priority rule here. When the white rocks showed up, the animal went into disruptive coloration. 80% of the visual field would tell the animal to go mottled, but instead it took the 20% of the information and went disruptive. So what's going on here? The idea, again, is that we think there are some visual cues here that are simple, and we're going to try and sort those out experimentally in part 2. All right, just to change gears, to wrap things up in a little different direction, and that is signaling. Signaling is the polar opposite of camouflage. These are high contrast, unambiguous signals. The sender has to deliver to the receiver an unambiguous signal, and that's the idea with animal communication, all communication for that matter. And they use this for a variety of reasons. But I want to point out an example here. You could see these 2 squids. These are Caribbean reef squids, and there's a male on the left and a female on the right. Now you can see that male is fighting right here, another male, so they're using their coloration and their patterning to conduct a fight, and the pattern on the bottom of the top animal and the top of the bottom animal are very different. The signal is different to the receiver and the sender depending on their position. So they will carry on these somewhat gentlemanly fights until someone wins, and then the successful male will pair with the female. So now you see the male on the left over here is showing one pattern to the female, and on his other side he's showing a white fighting pattern to any approaching males. So this is dual signal simultaneously, and if he shows the white pattern to the female, she's gone. And you see as they change places there, he very casually changed his pattern so he didn't frighten away the female with an aggressive pattern. So again, visual input is modifying the appearance of the animal here in a very social context. So put another way, we could say here you have right here 50 million years evidence of the two-faced male. So let's move on from that and see what else we've got going on here. And I want to talk about the key elements here about vision. To achieve the kind of changes that you're seeing, you need a good visual system, and you need the skin to implement that patterning and coloration change. So here we have another example of a cuttlefish at night. And the reason to show you this is to show you the details of the skin and how optically malleable this skin is, which is to say that if you look carefully here, and we'll zoom in a little bit, look at this white spot right here. It gets masked and then it turns on again. You see smooth skin, you see three-dimensional skin, you see transverse bars, you see spots. All of this is like electric skin. Here you have a very subtle change from a not so strong line to a very strong one, and a very strong, subtle, or a very subtle change from brown to a little less brown. And now watch this false eye spot appear on the back. This is a signal. So you get the idea that the skin can do a lot of things here, and we want to look at that feature in part 3 in particular. So, some summary thoughts. Coloration and patterning are absolutely widespread throughout nature. Our entire world is based on coloration and patterning for all visual animals. Rapid adaptive coloration has evolved to an extreme in this animal group. So the idea is whether or not we can pick up the principles of how they use this system and apply them elsewhere. So I'd like to point out this nice saying: organisms with extreme adaptations like this could reveal general principles. This was a famous saying by Auguste Crew, a Nobel laureate in the 1920s. I also want to point out, I really haven't made a point of this, that camouflage is really one of the key evolutionary mechanisms that occur on this planet. And there's predator-prey interactions. It's an easy thing for a human to understand because we are visual predators, and camouflage is something that's we're paying attention to a lot, whether you're a hunter or just admiring nature or you're a biologist. So the problem is that it is very poorly understood from the visual perspective aspect, as well as the principles involved in how it works. And there have been a lot of inappropriate assumptions. So camouflage offers us this unorthodox way to study visual perception. I'll talk about that in part 2 coming up. And signaling is the opposite of this, always exploiting the same number of small variables: texture, color, pattern, brightness, and so forth. Visual input is really guiding both types of behaviors, and that skin is controlled by the brain. I'll talk about that in part 3. And I particularly want to point out now as an overview that it's pigments and reflectors that create all the changeability in the skin. This is a really important point. Many folks will think that maybe it's just some set of pigments, or maybe it's just some set of reflectors in some animals. It's really the combination of the two that sets apart this animal group to give it this spectacularly diverse range of appearances. So with that, I'd like to close this part 1 as an overview and having posed a few ideas, and to point out this lovely phrase by Louis Agassiz that sits in the library of the Marine Biological Laboratory: "Study nature, not books." Thank you, and in part 2, we will delve into some of the visual mechanisms that really support this system.